So we stopped at being able to think about how to think about reducing the dimensionality of the data. And one of the sets, because there are multiple ways to do it, right? One of the constraints that we set it to is that the reduced dimensional space should have something where if I try to reconstruct it, I should be able to reconstruct my original space back with minimal error. Is there a concern here? Is there a concern in the middle? What's the concern? Okay. It's a friendly advice. Never take anyone for granted. Right? That's very, very friendly. Okay. So, if you see these are your data points in 2D, we want to reduce the dimensionality such that we can reconstruct with a minimal error. So what we do is we're going to say that let me find a projection. I'm going to project it into one dimension. How we do this, we'll see it in a bit. But you can think of this as an oblique line. It could be perpendicular. It could be some way this. But we'll get some line like this. Right? That's what the overall goal is. We have this data points in one dimension now. If we want to go back, we should ideally be able to go back to two dimensions, such that we're able to reconstruct the original space. And now there is no projection, there is no dimensionality reduction algorithm which will help you to reduce it to full extent, but we will try to do our best, right? So the simplest approach would be, you remember this angle with which you rotated it. You remember the angle of this line, and all you get back is you get back this reconstruction, right? So this particular reconstruction error, the amount of error that you have done is the distance between your original point and the reconstructed point. So these are your reconstructed points. That's the amount of error that you have suffered in the process. This is what 1D PCA tries to do. It tries to find out the projection. We'll see it exactly in a bit on how that projection is found. But any information that you're able to retain about how you got to that particular direction, that will help you reconstruct the original data back. Okay. Okay. So before we do some of it, it's just sometimes it's just good to know some linear algebra. I will not go too much into technical details, but you have all probably taken some course in linear algebra, right? It's a very one of those courses where you take it first time, you see like what am I doing, and then in the later on it hits you. That's all you really need to know. If you want to know anything about machine learning, you want to know anything about regression. That's one subject. If you know all of these things that you're going to derive, should follow straightforward. So the first concept that you should know is the concept of standard basis vector. The standard basis vector is something that spans the space, or the basis vector is something that spans the base, right? So if I'm in two dimension, if I start with these two vectors, which are my basis vectors, I can construct anything which is in 2D using, or anything in this particular space. It could be 3D, 4D, whatever. If I have the access to basis vector, I should be able to reconstruct any point in that space with these two vectors, right? So for example, in your 2D space, the reason you start with these axes is because any point anywhere on this space can be represented as a linear combination of two vectors. One is 1, 0, and the other one is 0, 1. So your normal xy, the way it comes is you're multiplying something by a scalar. This multiplied by first basis vector plus a scalar multiplied by a second basis vector, that gives you the vector in your 2D space. Okay. Then there are two concepts that you should remember, like broadly one concept that you should remember, that a term that has come up in the past, which is of orthogonality. Right? So the way orthogonality is sort of projected in this world, or sort of thought about as this world, is if things are orthogonal, they have extra amount of information, right? So if things are oblique, then some amount of information is going to be shared. The moment your vectors become like this, they are perpendicular, the amount of information that they're going to share is going to be practically zero, right? That's how we perceive it in terms of the linear, in terms of our world. So it's just defined as a dot product, right? So you have all probably seen this version. that if the dot product of two vectors, so in this case, the dot product of these two vectors is 0. Everyone understands what the dot product is? That's what you get if you multiply these two vectors, right? Again, these dimensions are such that I get back the original dimension of the vector, right? And if this is 0, then that becomes those two vectors are orthogonal to each other. The orthogonal basis is a set of vectors. So the choice that I did here was orthogonal. You could have chosen slightly different vectors as well. The reason we chose orthogonal vectors is because the amount of information that they share is non-redundant, whereas if you have oblique vectors, there is some amount of information sharing happening. And it's fine if you don't understand all of it. Just try to get the idea is to just get an intuition about what we're trying to do. Right? Is this idea clear? You want to represent anything? You can start with the two-dimensional with two vectors which are perpendicular to each other. In other words, they are orthogonal. Hence, they form an orthogonal basis. They form a basis because any vector in this entire space can be represented as the sum of these two vectors. And finally, you have this term of orthonormal basis, right? So, if two vectors are orthogonal and their magnitude is 1, then they become orthonormal basis. Okay? The term probably will mention it last time in the class. It will make one more mention, but if you understand it, it is fine. If you don't understand it, that is also fine. Okay? What it is essentially trying to tell you is you can represent anything rather than the vector, this particular magnitude being anything, you choose it to be a 0, 1 and a 1, 0 vector. That's the orthonormal vector, orthonormal basis. Any questions about this part? Okay. Okay, so fine. So we have some idea about like geometry. We have some idea about linear algebra. We can now start to flush out our problem, right? So these black dots are again the points that we started with, right? And we said that we want to be able to construct a lower dimensional representation of it. We want to be able to do this such that the reconstruction error we get is minimized. Okay? We want to make minimum amount of error if I want to reconstruct it. So let's assume our projection looks like this, right? So this is your original point. This is your projected point. This is the amount of error that you're going to construct. When you reconstruct it again from this point, this is the amount of error that you're going to waste because you're not going to be able to get the actual point back. This happens to be projected, right? So any projection, whenever you hear about a word projection, it is if you were to take this point and if this was a mirror, you will make a perpendicular angle there to sort of see, actually the mirror is somewhere in between. You will see where exactly does that point land, right? So if you're basically projecting this point onto this axis, you will land up with this point, and this angle here is a 90-degree angle. Okay. This is quantified in the term of r. Now, if I complete my triangle from here, so this is the amount of error that I'm going to make, right? So this is whatever r. It's a two-dimensional vector, so I can write this as sum xi minus xi bar plus sum yi minus yi bar. We don't worry about that right now. All we worry about is that we have a vector with which we can represent this difference. Now, if I center my data first, right? So in all the discussion that we are going to do, we're going to assume our data is centered, right? So the mean is 0, the standard deviation or the distribution or the covariance can be anything, and we'll see this in just a minute. So if the standard deviation is whatever, but the mean falls to 0, so that's why this is 0, 0, both for x and y axis. It's easy to understand in 2 dimension. You can always mean center your data so that this point is 0, 0, 0, 0, 0, right? If it's a matrix, all you do is you subtract the column means and you get a vector which is going to be mean center. Is that point clear? We'll see this in just a bit why it has to be mean center. But you can always subtract one fixed quantity from anything, right? So if you remember assignment 1, I had used this word offset, right? So if you have certain set of observations and you want to study them, as long as you subtract or add something to it, you can always do those kind of operations because why? It doesn't affect what? Adding something to same quantity to all the things, what does it not affect? It doesn't affect the variance, right? That's what we mostly care about. It will affect the mean, but it will not affect the variance. So we can always mean center it. I can always say that this is offsetted by x value. So if your scores are minus 180 minimum, I can always say that this score is between 0 to 900. It's fine. It's offsetted by 180, right? If I want to study the distribution, because not all distributions will have negative values, right? So people who did not get that hint, I think most of you probably would have gotten it. That is what I meant by that offset. So this is offsetted to 0, which means that it is mean centered to 0. Now, if I draw these vectors, right, this is some diagonal D, this is your reconstruction error, and this is some vector V. Okay. Now, if this is mean centered, what is, if this point is x bar, what is x bar? What is this value? So it is centered here, right? So this is again a vector. So I'm with slight abuse of notation, I'm making it a square, subtracting the mean from it. So this is a measure of what? Does everyone see? Why is it variance? Right? So this is some, again in two dimension, this is some vector. I know its mean is 0, comma 0 and subtract the variance. Right? So people who have seen version of this PCX is a slightly different formulation than what it was. Okay. Right. So this is a variance version, variance form, right? So I wanted to minimize this, right? So I want to make it as small as I can. What does it entail? Like what does it collapse to? So this alleyway is a right angle. Geometrically, what does it mean? Yeah. Exactly. Your D, which is your distance, right? So your D is tends towards P. That's what you're trying to do essentially. So essentially, if you want to minimize this, you're trying to sort of push that point as close to possible as to the original x. There's a different formulation to see this, which is I can take any other axis, like I've been forcing you to think in this direction. You can do this, you can take any vector and try to do this minimization operation, right? And that's what the code that I'm going to show you, and you will do this also as an exercise. We'll try to sort of follow. Okay? So minimizing the reconstruction error is equivalent to maximizing this variance. Does everyone see why? So I want to minimize this R. Okay, this is just geometry, right? This is just your high school geometry of hypotenuse square being equal to sum of the two sides square. So minimizing the reconstruction error is very like we're not doing any formal math here, right? But intuitively, does everyone see why minimizing the reconstruction error is equivalent to maximizing the variance once you have mean centered your data? Clear, everyone? Any question? Anything that is not intuitive? Anything that's not clear? Yes. Why is it related to variance, right? So what is this? What is this point? It's some x bar comma y bar. This point is a projection of this point. Okay. You have mean centered your data. This is your reduced dimensional space. Minimizing the reconstruction error is equivalent to maximizing the variance of the projected point. I should have added that. Okay. So these points, these values that you're going to get, they are still going to be mean centered, right? Because your mean is 0. So you're not doing any adjustments here, right? So the mean is not going to change with any sort of operations, right? Because all we are doing is we are doing some sort of rotation, right? Whatever this was, I want a one-dimensional representation, so I'm going to find it somewhere. It's just going to be a rotation. So what does rotation mean with a vector? What does it mean? How do you rotate a vector? What is the operation that you do? This you should be able to just intuitively also do. So vector, how to rotate it? Multiply by some function, right? Some cos theta, sin theta, some vector which has some magnitude, whatever, 1, 2, something. But all you're doing to this is you're just scaling this by a constant, right? Whatever that constant is, you don't worry about it. So I'm doing some sort of operation which is EBX. So the mean is always going to be this point, which is 0, 0. Even if I rotate it, whatever I rotate it, mean is always going to be that this point. Okay. The variance is for the sorry, I should have been a bit more clear. The variance is with respect to the projected point. If I want to minimize this, I'm essentially going to maximize this, which is equivalent to maximizing the variance of the projected data. So I'll just spell it out. Okay. So essentially what the axis that you're trying to find is that axis along which the variance of your projected data is going to get maximized. Okay, does that make sense? And intuitively, what would that direction look like? What is that going to be that direction where the variance of the projected points is maximized? Intuitively, where should it be? And the point itself, which is the original point itself, or the shifted point. Sorry. So one second, I'll just use sorry for my drawing again. So let's take your data looks like something more complicated than this, right? What do you see in this data first of all? Like what is happening? There's some variation in this direction, right? There is some variation. If I go in this direction, there's some variation. But if I go here, the variation is somewhat very, very high, right? So if I somehow make a line which can pass through all these points in some fashion, the projected points will all lie along that lines and will end up maximizing the variance somehow. Does everyone see what I'm talking about? Or is that not clear? So what direction will this likely be? So why am I drawing this vector, right? Why am I not drawing this vector? Why am I not drawing this vector? The reason for that is because there is something special about this direction which you see. You can see that if I somehow can go, only if I had access to this one direction, I will see that there is a lot of variation happening here, right? There's a lot of variation happening in this direction. And that's the direction that you want. Because you want to minimize the reconstruction error, which is equivalent to maximizing the variance, which happens to be actually in a direction intuitively, right? There's no mathematical formulation that you're going to do. It's going to be intuitively in the same direction where you see a lot of variation happening in the data. Okay? Everyone with me so far? Okay. Okay, so let's try to formalize this somewhat, right? So we saw a variation of this along that where we try to sort of break down the variance in this formula, right? That variance of sum of random variables is equal to sum of the variances as long as the as long as what? Variance of sum of random variables is equal to sum of the variances of the random variables as long as they're independent, right? Okay. So in this case, if they are independent, what essentially happens is one does not inform the other, right? So if you measure one, they are independent, so you don't know exactly what is going to happen to the other one, right? So in a way, these are like perpendicular. If I measure this thing, I have absolutely no idea what is going to happen in the other direction. There is a concept of covariance, which is a measure of, essentially a measure of information, right? It's a very good thing to have overall. It's a measure of how much one thing informs you about the other. The covariance is nothing but just the formula of variance, but applied to two different random variables, right? So variance is e of xi minus mu whole square. This is e of xi minus mean of xi multiplied by multiplied by xj minus exj, right? So this is just variance, but the random variables are different. Let's try to visualize what does a variance covariance look like. So imagine you have only two random variables, right? You can calculate if you have x1, x2, you can calculate four values. What is the covariance about with x1, which is what? Just the variance of the first random variable. So I call it sigma 1, 1. There is sigma 1, 2. There is sigma 2, 1. And there is sigma 2, 2. Okay? Anything that you can figure out, what is there any relationship between these two? They are going to be equal, right? Very, very easy to see, just the formula. So if you know anything about one, you can know something about the other. So let's take this example. If this matrix looks like 0.2, 1, 0, 0. Intuitively what is happening, right? So intuitively, within the first variable, there is not much variance. This is a measure of the variance. So this is going to be constricted. In the second one, there is enough. So it's going to be much longer. Right? So this is 0.2, which is your variance here, and this is much higher. Does everyone see that? And there is nothing here, practically nothing here in this direction or any other direction, because this does not inform you what this will look like. Okay? Very simple to see. These are just vectors. Now, if I take 1 and 0.3, right? So in this direction, this is going to vary around overall, right? Again, take your normal case. So most of the information is going to stick around plus minus 3 times, right? So less number of points here, but mean of the point will be 50% of the points will be plus minus 1, right? Very loosely. Now this is negative. So what does it tell me? That if this increases, right? If x1 increases, this has to go in the other direction. Right? So if x1 increases, it's going in the other direction. Similarly, if y increases, it's going in the other direction. So this can be a negative quantity. Variance, if you remember, that's going to be positive. But this is always going to be positive definite. Or in this case, it's going to be a number which is going to be always positive or greater than equal to 0. This can be less than equal to 0, this can be equal to 0, or this can be positive. Okay? And finally, you have this Gaussian case, right? This is what a Gaussian cloud would look like, where nothing informs anything. They look very symmetric around the x and y axis. Is the intuition clear? Right. So all of you have seen covariances in some format. This is just formalizing what does it really look like. We can push this a bit, and we can see what do we really learn about our data from the covariance matrices. Right. So they generally capture the general extent of the data. It doesn't mean that if this is 1 and 1, it has to have this kind of a spread. All it tells you is how much do you gather in terms of the overall structure of this data. So you should interpret it in a more sort of a fashion in terms of how much does this inform about the other. It doesn't actually explicitly talk about this spread or this spread. Right? So these two matrices are exactly the same, but the spread is very, very different. Right? Similarly in this case, these are both diagonal. But the spread is one does not inform the about the other, and that's why these diagonals are 0. Right? Intuition is clear, very geometrically interpretable so far. Okay, why am I talking about covariance matrix? What role do you think it plays? in helping you figure out what is the right dimensionality. And how can we use this information? There is so much information here, right? The meat of the information is here. Anyone with some intuition about how can it help us reduce the dimensions? That's the goal we were talking about, right? And then I took you on this tangent about talking about covariance matrices and showing you what does it look like. What does it really tell you about the data? Say that again. Okay, interdependence. What's your name? Srishti. Okay. And Srishti B, right? What's your last name? B. Okay. Um, okay. Good. Right. So it tells you about some sort of interdependence, and the reason you want to be able to leverage this is because you are thinking about reducing the dimension. Right. We are thinking about how to sort of reduce this dimension, talk about. So intuitively, we'll see the recipe of PCA, right? So the reason it's going to be a recipe is because, well, there are a lot of mathematical operations, and they're like they'll do some math, but then it gets, some feedback I got is like just getting too mathy for an introductory course. So I'll not talk about like full on math, but I just wanted to give you the intuition about how does it exactly work. Right? So imagine you had this covariance to begin with, right? And I'm trying to ask that I want a reduced dimensional representation of this data. So what does PCA do? So all PCA is doing is, so this is your covariance visualization by the way, this is not your original data. It's trying to essentially look for the direction where if I capture that particular direction, what essentially I'm doing is I'm essentially rotating this covariance matrix, right? Such that the directions that I capture, they end up maximizing the information that I have. Right? So if I do my PC operation and I rethink about what a covariance matrix looks like, it becomes, at least in this case, I can make the diagonal entries go away. So if I just even retain this axis, I can still retain a lot of information about it. Rather than being, sort of drawing an axis, in this case, again, this is covariance by right, this is not the raw data, any other axis, right? In which case, it will not be able to capture this much level of variance. You can do this as an exercise. I'll show you also an example of what the illusion is. So far, intuitively, is it clear what PCA is doing? So this you should know, right? Whichever data science interview you go to, whichever whatever, like however hard machine learning you like, how does PCA work? That's the basics of a lot of techniques out there, right? So even if you don't know the math, just try to understand intuitively what is it really trying to do. Right? Any data science interview, any data science class, anything that you do, this is the basic thing that intuitively what you're trying to do. Any questions? Okay, right. So there is an SPD theorem, right? So that's where it starts to get a bit mathy. And the theorem is very, very nice, right? It's a very beautiful theorem. It says that you give me any matrix, doesn't matter it's vertical, doesn't matter it's rectangular, doesn't matter it's a square matrix. I can break it down into these three special matrices. These three special matrices are U, S, and V. Okay. Why are these three special matrices? Because S is a diagonal matrix. Okay. Which means that essentially I can start from any matrix, right? Any matrix in this world, I can start with any matrix. I can break it down into some long form matrices. And what it essentially tries to tell me is, should be slightly longer, is this is always possible. Always you can break it down into very special category. The reason this is special is because this is a diagonal matrix, so its entries are ordered. We'll just call them sigma 1. I have to figure out how to not make it squeak. Okay. Yeah, I think it has to do with the quality of the chalk. Okay, and in terms of U and V, these are also special. Why? Because if I take UU transpose, this is an identity matrix. which means that I will again get a diagonal matrix which has all ones, zeros here. Similarly with B, this is an identity matrix, right? And you can figure out the dimensions based on what those dimensions are. This is M cross N. I can break it down to M cross S, S cross S, S cross N, where S are your non-zero single. These are called singular values, right? So why is it beautiful, right? Like it's a very powerful thing. It says that we'll see like geometrically what it is doing, but the reason it's powerful is because it says that give me any matrix, I should be able to give you a space in which all these are your orthonormal vectors, right? So this is the way base in which you are representing. This is V transpose. This is the base in which we are representing. I can from any beginning, which is like it can be any space. It could be collinear. It could be collapse. It could have like things which are going to relate to each other. M does not have to be equal to n. I can reduce it in such a way that things can be represented in the form of a particular space. Like all these vectors are perpendicular, and the reason it becomes geometrically possible is because what essentially SVD is trying to do is it's trying to rotate the matrix. We'll see the visualization in just a bit, but this is just geometrically what it is trying to do, right? So any matrix which is of U sigma V size, which is of M comma N size, can be broken down into three special matrices. Right? So you put a matrix, it gives you a set of numbers which are called singular values. The entries of that sigma value are ordered. So sigma 1 is greater than sigma 2 is greater than sigma 3. And we'll see what is the interpretation of that in a bit. And this gives you a vector which is in high dimensional space. Okay. The V is called the right singular vectors, U is called left singular vectors. The naming, I don't care about it, right? All you need to know is geometrically what is happening. Okay. So far, everyone with me? People probably have seen this already, right? Or some version of SVD. So any machine learning thing you're doing, right? Any fancy matrix operation you're doing, this is the core, right? This is the core of all these algorithms. So let's just very quickly geometrically see what is happening. So imagine you had your original data, right? So if you have any standard basis vectors, a matrix is nothing but an ellipse, right? It's an ellipse because any number in at least 2D, 3D, whatever, it's either an ellipse or an ellipsoid. In the best case, it's a circle. What SVD is trying to do is it's saying that to get this ellipse kind of information, you can start from these standard vectors. Let's rotate it a bit, rotate it in a basis so that maybe you don't get back your standard basis vectors, but you get again special vectors which are perpendicular to each other. So rotate the standard basis vectors this way, scale it, right? Scale it because I know in the end I want the matrix back. Scale it so that I get an ellipse. So this is what the ellipse that you get, and do one more rotation. Do one more rotation with a new vector, which is u, so that you get your original matrix back. Any matrix in this world is basically visualizable as an ellipse or an ellipsoid or whatever, like whichever dimension it is. In 2D, it's an ellipse, right? You can draw it. This is what it will look like. This stretch determines, how different those two vectors are. To get this, what it is saying is, I can start from, you can give me a basis vector, standard basis vectors, I will rotate it, I will scale it, and I will give it to you back. Right? In the process, what have I learned, right? What am I doing this? In the process, I have learned how much should I stretch this by, because that's where my information is. Okay? Any questions? Any questions about geometric interpretation of SVD? The most beautiful theorem that you need for anything that we're going to derive from now on. Okay, so just see an example, right? So this is a matrix. Again, you can ideally, if this is 4-dimension or 3-dimension, you cannot draw it, but this looks like an ellipsoid. It's rectangular. There are 3 non-zero singular values. Don't worry about how these values are derived. We'll use computation to derive it. The rank of M is 3. What is the rank of M 3? What is the rank of a matrix? Number of? Okay, visually what is it like? This is a 4 cross 3 matrix, right? Or 4 cross 4, 4 cross 5. So what is so special about 3? Okay, good. Okay, right. So three is the amount of like, in a way, these are the dimensions that you require ideally to capture everything that's there. Everything else is can be represented in the form of those three vectors, right? Right. Fair enough. Yes. Yes. Where are we starting from? And what is the direction that we're taking? So what we are starting from is you're given this thing, and you are figuring out how on earth did I get this matrix? Okay. So this is your high dimensional matrix. This is your 3, 4, comma 5 matrix. I'm giving you the recipe of how can you create this matrix. What is that recipe? Start with a standard vector, multiply it by something called v, which is the right singular value, scale it by sigma, again rotate it, and that's how you get it. In the process, I've learned two sorts of information. One is what is this vector, which I can sort of use to scale it. How much should I scale it by, and then how much should I rotate? I honestly don't care about whether I rotate it or not, because the moment you are here, you know everything about that matrix. Does that make sense? I saw a version of this where the scaling was happening when those two arrows were solved. So it depends on like how you want to scale it, right? So here I'm doing it in this direction where I'm multiplying sigma by d bar or d hash. Other people can also use u sigma and multiply it directly, which means that you will start from this rotated vector and directly convert it to this. Right? So it depends on how you're doing the matrix operations. Okay. And they say that those arrows are along the direction of variances of the data. Right, so that we'll see in just a bit. Yeah, that's basically what it is. Like your single values are like these are the directions which have your neat information, right? That's where you need to how much you should stretch. So if you want to make an ellipse from a circle, you need to know in which direction I need to go, and that's the direction that you're trying to figure out because that's where your information is. So this sigma one, it's always going to be greater than equal to sigma two because it's stretched in this direction, right? That's the direction I'm trying to figure out. Okay, everyone with me? Okay, so in the process, I can figure out what is the rank, which is how much dimensionality is there in my data. This is my SVD. Okay, so what are like this follows up to your question, right? What is your what are really thinking? What is really a singular value, right? So these are values which are the non-zero singular values that you got from your previous matrix. These are your scaling factors. These are the length of these axes which are useful to help you represent this data, right? So when we learn this, that's the amount of information that we're capturing. That how much do I need to perturb it to get to that particular thing? That's what we're trying to measure overall. Okay, then there's one more theorem. Don't worry about this. Okay? So don't worry about how it's derived. Don't worry about how it comes. Just make sure that you understand what it is trying to say. So it's saying that if you have a matrix, you know that any matrix in this world can be decomposed into this format. If I asked you that you start from a 5-dimensional matrix, lot of information, right? Lot of information in the 5-dimensional matrix. Give me a 3-dimensional matrix such that the amount of information that has is maximized. Young-Descartes theorem tells you how to do it. And that's basically based on SVD, right? So again, you cannot imagine 5 dimensions. Imagine you start from an ellipse, or imagine you start from an ellipsoid in 3 dimension. I ask you, give me a 2D reconstruction which captures as much amount of information, right? So with my poor drawing, we'll try to visualize it, and we should be able to do it in 2.5 minutes. Right? So ellipsoid would look like your egg basically, right? So you visualize this in 3D. I cannot draw the 3D version of it because my engineering drawing grades are like abysmal. But this gives you some version, right? So if I ask you that is imagine this egg is in 3D, right? And give me the best 2D version of it. Like what intuitively what will you give me? Such that the amount of information, imagine that egg has a baby, right? And you have to take a slice of that baby. Let's just imagine you have to take that slice of the baby. What is that slice that you will give me so that the amount of meat you're going to, okay, some of you don't, okay. The amount of egg that somebody can eat is maximized. What is going to be that slice? Right, so the egg is like this, right? So intuitively, it has to be, you have to do a okay. You have to do a top to down cut of an egg, right? That's what your SVD is doing. So what SVD theorem tells it is it tells you the direction in which you have to make that cut. So the amount of egg that you get gets maximized, right? That's intuitively what you're trying to do. Is that clear? So kill don't have to kill any baby. You're just killing a baby which never existed. That's what most of the eggs are. So excuse my whatever that whatever that tendency is. The idea was to tell you how those sort of characters are. Okay, everyone with me so far? Okay, so I guess we'll have to stop. We still have a few things to cover. Okay, next class I will resume from here where we'll quickly talk about this and then we'll start into regression, do some very basic machine learning. Uh, we'll have a guest lecture next Friday, so 14th February. Two guest lectures back to back in class. So please come. Your assignment will be out. Next assignment will be out today or tomorrow. Will be due in 7 days from whenever it is released. Okay.